Hi folks, Mr. Ackerman here. Thanks for watching. The topic of this video is experimental uncertainties, sometimes referred to as experimental errors. And what this topic is actually quite important as far as our lab skills go, because as you're going to be doing in physics class especially, you're going to be making a lot of measurements involving some of the basics like length, time, and mass throughout the course. And whenever you do a measurement in science, I know you like to think that you measured something exactly. In fact, maybe that's what attracts some of you to science, the fact that it's got this, this air of exactness to it. However, as you're going to see, hopefully after this video, whenever we make any kind of measurement, we never make an exact measurement. It's actually impossible to do this. We always have some sort of uncertainty in terms of the final measurement. And maybe the best way to illustrate this is with an example which I'm going to get to in a moment. So hang on for 1 second. Let me just tell you what we're going to be doing. We're going to be talking about what these uncertainties are and how they arise, and also how you perform calculations involving them. If you're following along in the schedule, we're still in lesson 3, projectile motion. We're actually right in the middle of this lesson. We've done horizontal launches, and now we're about to do a lab called the ball bearing bounce, which is in your course pack. However, when we do this lab, we are going to make measurements. We're going to make distance and time measurements, and I'm going to ask you to incorporate this new idea of experimental uncertainties into your lab analysis and your write-up. So that's where it says here, Introduction to Experimental Uncertainties, Course Pack, page 7 to 12. Once all that's done, we will resume with projectile motion with the non-horizontal launches. All right, so anyway, getting back to the little intro that I was, little introductory story about how measurements can never be 100% exact, how there's always some uncertainty. Let me try to convince you that this is the case, and that even though we're all scientists and we like to think we are exact, we aren't. Here we go. On this slide, you see two diagrams. I'd like you to focus on the upper diagram first. This top diagram is actually a microscope image of the edge of a razor blade. Now, you and I both know razor blades are extremely sharp. If you look at them with the naked eye, they look like they're very straight, and you wouldn't put your finger near one because you'd get cut. But when you look under a microscope, look at what you see here. The edge is actually anything but straight. It's actually quite jagged on that scale. So now, consider this proposition. Suppose you are in a lab and I ask you to measure the length of a razor blade, or how wide it is. And so you take a really fine ruler and you hold it up under a microscope and you measure where the edges are and you come out and give me a number. Well, how exactly would you do that, considering the fact that the razor blade actually isn't that straight, it's quite jagged? What would you put as your answer for the length? You'd have to put sort of like a best guess for maybe an average length, with a little bit of a range over which the true answer may lie. Now, let's look at another example. The second picture here is just a diagram. Some of you may recognize this. It's kind of a grade 9 kind of particle theory of matter diagram rather. And if you remember the particle theory of matter, that's where they say that all matter is made up of these tiny particles that we call atoms and the molecules, and that when all of these particles are in constant motion. They can be in a solid form, a liquid form, or gas. That really is only determined by how fast the particles are moving. If they're moving pretty slowly, they don't overcome the attractive forces between them, and they stay pretty much together in one solid piece. This is what we call a solid. If they're a little bit hotter and therefore they have more kinetic energy and they're moving faster, they can pull apart a little bit and then we get a liquid. And of course, if they're really hot, they can move fast enough to overcome the attractive forces between the atoms or molecules, and then they fly around all over the place and you have a gas. All right, there's your review of grade 9 particle theory of matter, but what I want to do is focus on those solids. Over here with the razor blade, I asked you to measure the length of a solid, and we looked at some of the challenges. Suppose you said to me, all right, I'll tell you what, Ackerman, give me a really fine, smooth, sharp edge of some substance, and then I can tell you exactly what its dimensions are. I'll look at it under a microscope, I'll use a really fine ruler, and that's how I'm going to do it. Well, at some point, you would be getting down to the level of atoms and molecules, which, according to the particle theory of matter, are in constant motion. And then I would ask you again, where is the edge of something whose component particles are always moving? You couldn't tell me where the edge is. And so I hope you're starting to realize that at the most fundamental level, there is no answer to the question, what is the exact length of something? Therefore, whenever you tell me the length of something, what you really should be giving me is what's called your best guess. Oops, sorry about that. You should be giving me your best guess and some sort of range over which the true answer lies. And this is an important concept. Don't ever forget this. This is the whole concept of experimental uncertainties. The best guess is exactly what it's called, best guess, and the range is what we call your uncertainty. As an example, you might write something like, I think this razor blade is 1.35 centimeters across. However, the range could be anywhere from 1.33 centimeters all the way up to 1.37 centimeters. Well, if you told me that, then here's how we write this as scientists. We would write 1.35 centimeters plus or minus 0.02 centimeters, and this plus or minus 0.02 would encompass the range of up to 1.37 and down to 1.33. And so this is how we write experimental uncertainties. Best guess plus or minus a range in which the true answer likely lies. Okay? Now let's take a closer look at some of the devices you'll be using in this course to make measurements. You're going to use rulers to measure length. This is one of the basic measurements we can make in the universe. You're going to use stopwatches to measure time. This is another basic measurement that we can make in the universe. And the other one, of course, is mass, another very basic unit of measurement in the universe. So let's take a look at the ruler as an example. When you measure the length of something, what you usually do is you take one end of that something and you line it up really carefully with one end of the ruler. And then what you do is you look for where the edge of the object is and you line that up with the other end of the ruler and you make a guess. Now imagine we're talking about the edge of something that's really fine, like a sheet of paper. This ruler has inches, which we're not going to talk about. It's on this side got millimeters and centimeters. That's what we are going to talk about. So please just focus on this side. The edge of a sheet of paper, you could probably tell me for sure to the nearest millimeter where it is. Like you might say something like this piece of paper is, I don't know, 20.1 centimeters long. That would be like saying 20 centimeters and a millimeter, 201 millimeters, right? But could you ever do better than that? Like, could you pin down to the nearest hundredth of a centimeter where the edge of the piece of paper is? I doubt you could do it. The nature of your measuring device and the nature of the edge of a piece of paper makes this very difficult. And so, now you might also be thinking this kind of relates to sig figs, and you're right, the two ideas are related. But what I'm talking about here is when you say, okay, here's the best I can do reading this edge of a piece of paper, so I'm going to throw that out. You might also run into a problem that some rulers are, they're a little worn out, or maybe the edge of the piece of paper is a little jagged. It wasn't cut very well in the paper making factory, the paper mill. And so you might say, you know what, this is my best guess, but I realize that it's possible that the true answer lies over a range, so I'm going to give you a range, and now the question is, what are you going to use as that range? Well, there's two things that go into estimating this range. One thing is called the instrumental error, and the other thing is called the statistical error. First, we're going to talk about the instrumental error. As a general rule, the instrumental error is half of the smallest division of the measuring device. So if you're using a ruler that measures to the nearest millimeter like you see up here, then half the smallest division would be 0.5 millimeters or 0.05 centimeters. And the idea here is that once you get into divisions of the smallest division on a measuring device, you're really starting to estimate where the true answer, the true measurement lies. So as a starting point, we usually always add in at least half the smallest division as an uncertainty. So here I would add in for instrumental error, i.e., let's say 0.05 centimeters. The statistical error is something different. And to see what statistical error is, let's just put the ruler on hold for a minute and let's look at the stopwatch here. I'll use a different color so that you can keep track of what's going on here. For the stopwatch, suppose you are measuring times, like maybe you're timing a race. Maybe it's the 100-meter dash. And maybe a student at your school, an athlete, is able to run the 100 meters in, let's say, 13. Well, on this stopwatch, it looks like you can measure to the nearest hundredth of a second. So let's say the student ran the 100 meters in a 13.75 seconds. However, let's also assume that you're not the only timer. Maybe you're trying to be as accurate as possible, so you ask two other people to independently measure the time. And let's say they watched the same runner at the same time in the same race, start at the same time as you did, and finish at the same time as you did. Do you think they'd get exactly the same answer for time? I think you know that they probably wouldn't. Someone might answer a little bit higher. Someone might answer a little bit lower. Well, how can three people who are all watching the same thing measure three different times? Well, obviously, reaction time enters into it, judgment, the idea that you have to see the person start and see the person finish, and your brain has to send a complex series of signals to your thumb to stop the timer. And this will be different in different people. It might even depend on how much sleep you got the night before and whether you're awake or not when you're observing this. Well, the fact that we can't agree on the exact time means once again there will be some uncertainty. And this kind of uncertainty is what we call statistical error. As in, statistically, we're just never going to measure the exact same times. There's a certain spread. So how might you deal with this? Well, I don't know, maybe you would take the average as your best guess. And here I am, again, not as prepared as I could be. I'm doing this on the fly here, so I'm going to calculate the average by hand here. 1375 plus 1383 plus 1368, and then I'm going to divide that by 3. And of course, my calculator is, I'm not using my calculator today, I'm using someone else's, and it's giving me a fraction, which is not what I wanted. I wanted a decimal. Here's my decimal. It said 13,753, and the 3 is repeating. So there's the average there. But there is a range over which the true answer probably lies because 3 people had 3 different numbers. So what might you do here? Well, there is a complex branch of mathematics that tells you exactly how to deal with the statistical error. But just as a starting point, maybe we could say 1375 will be our best guess in seconds. But since one of the numbers is about 8/100ths of a second higher than the average, and the other one is about 7/100ths of a second lower than the average, I don't know, maybe plus or minus 0.08. Will that take care of all of the measurements? Sure, that would cover everything. So there we go, we have a statistical error. Of course, the stopwatch also has small divisions. The smallest division in this stopwatch is the 0.01, the hundredths of a second column. And so just like we used half the smallest division as an instrumental error on the ruler, you might also say half the smallest division on the stopwatch. as an instrumental error. And what you might do is add the instrumental error and the statistical error to get a total uncertainty or total error on your measurement. This is something that you can do. You don't always do that. In this case, the dominant error seems to be statistical. It's many times greater than the instrumental. So for the stopwatch here, you might ignore the instrumental error. It's really so small compared to the biggie, statistical. Let's go back to the ruler here for a sec. Here where you're measuring length, there's nothing statistically difficult about measuring the length of the piece of paper. I mean, it's a very controlled environment in a lab. You put it down, put the paper down on a table, and you measure the length, and that's pretty much it. Many people aren't going to get very different answers than you, so there might not be a lot of statistical error in this measurement. Maybe for this, you would only put the half the smallest division uncertainty. Okay, so this might be your answer for the length of something, like a sheet of paper. This might be your answer for the length of time for someone to do something a little harder, like run the 100 meters. And the same thing goes for measuring mass. Mass is probably more like a ruler kind of measurement, but I hope you get the idea that there are instrumental and statistical errors. And now the question is, what do we do with these numbers once we have them? So, first of all, you're going to be taking numbers in this class, and of course you're going to be adding and subtracting them. For example, someone might say, okay, I have measured 2 masses and I want you to add them. Suppose we've got 13.92 grams plus or minus 0.08 grams. And maybe this is the mass of some object that we are adding to some other object at 7.34 grams plus or minus 0.06 grams. How would you add these two numbers? Well, easy. First you add the two best guess portions. These are your best guesses. Adding is still adding. BG for best guess. And what does that give us? I'm going to cheat here just to save some time. I'm going to use my calculator instead of my brain. 13.92 plus 7.34. I get, oh, there we go with those fractions again. Okay, here we go. I've got 21.26 grams. But what is the uncertainty? Well, if this first number could be higher or lower than my best guess, and this number could be higher or lower than my best guess, then I guess this number could actually be higher or lower than my best guess, right? Like this 1392 could be this much higher. What would this put it at? It would put us at 1392 plus 0.08. That would put us as high as 14. And what would this go up to? 7.34 plus 0.06. That would put us to 7.40. Adding these, I'd get 21.4, right? Which is actually a bit higher than this, about 14 hundredths of a gram higher. Where does that come from? Simple. Add this to that. Add your experimental uncertainties when you are just adding values. Okay? And that's it. Using the same logic, this number could be as low as 13 point... Oh, sorry, I've got a phone call coming through, folks. Hold on a sec. 10 minutes? Yep. There you have it. Teachers are people too. We actually use the telephone, believe it or not. I've even heard that we sometimes go out to the movies, but that's yet to be experimentally confirmed. Anyway, back to this. 1392 plus or minus 0.08 could be as low as 1384, right, on the low side. And 734 plus or minus 0.06 could be as low as 7.28. Add those two together, and what are you going to find? You're going to find that it is actually 14 hundredths of a gram lower than this number. It's going to come out to 21.12 on the low side, which is minus 0.14 off of this number. Okay? So that should help convince you that if you're ever adding two numbers, two measured values that have an uncertainty, just add the uncertainty and you get your final answer. Subtraction works the same way. I'll leave it to you to try an example with the reasoning that I showed you for adding, but in order to save time, I'm not going to show you subtraction here. I'm just going to tell you that it follows the same rule as adding. Add the uncertainties. Of course, subtract the numbers to get your best guess, but add up the uncertainties and you'll be there. All right? Final thing that you might have to do is to multiply or divide numbers. So to give you an example here, in fact, I'll use an example that you're going to use in the lab that's coming up. Recall our lab that's coming up is called the ball bearing bounce. In this lab, you're going to be measuring velocity, the velocity of something. And the way you're going to do velocity is you're going to say average velocity is displacement over time. And in fact, the object's going to be moving in a straight line without turning around, so it'll be more than acceptable to just measure average speed. We don't have to confuse the matter with vectors, so let's just do an average speed calculation. So here you have to divide. You have to divide a distance measurement, which you may get using a ruler, the way we discussed over here. And you're going to divide it by a time measurement that you might get using a stopwatch like we discussed over here. So you know what? Let's pretend this is the distance, and let's pretend that this is the time, just so we can use some numbers that we already have looked at. 20.1 plus or minus 0.05. So 20.1 centimeters plus or minus 0.05 centimeters. And we're going to divide that by this number here, 1375 plus or minus 0.08. So here we go, 1375 plus or minus 0.08. Okay, now, the good news, dividing is still dividing. For this part, you still just divide the two numbers so that 20.1 divided by 13.75 going to give you, I get on my calculator here, 1.461 blah blah blah. That'll be centimeters per second. That has not changed. How do you deal with this? Some of you might be tempted to just say, well, just divide them as well. Just go like this. Well, if you do 0.05 divided by 0.08, you get 0.625 centimeters per second. And now I'd like you to pause and think about this number for a sec. Let's look at where it came from. This came from dividing these two, which came from here. 20.1 plus or minus 0.05. Here's what I'd like you to do for a second. Compute that as a percentage. What is 0.05 as a percentage of 20.1? So I do 0.05 divided by 20.1, and I multiply by 100, and I get a very small percentage. It would be 0.05 out of 20.1 times 100. I get about a 1/4%, not very much. And let's do the same on the time part of the equation. 0.08 divided by 1375 times 100. Here I get also a small percentage. So all I'm doing here is trying to put these numbers in perspective by using percentages. So we've taken two pretty well-known numbers, pretty accurately measured numbers, only a 1/4% uncertainty, only about 0.5% uncertainty. If we use this method for dealing with uncertainties when we divide, then this is what we get. Let's see what this is as a percentage of that number, of the best guess. It would be this divided by that times 100, which would give you, I'm just going to plug this into my calculator now, bear with me, 0.6 0.625 divided by 1.461, sorry, I had a typo there, 0.625 divided by 1.461 times 100. Here's what I get. You ready? Yikes. Does something strike you as odd here? I hope it does. You guys are all numbers experts. You deal with numbers in your studies all the time. So I hope your radar is picking up something here. How the heck do you take two pretty accurately known numbers, divide them, and end up with a disaster of an uncertainty? This is terrible. This is like saying, let's meet for dinner. I'll meet you at 7 p.m. plus or minus 3 hours. I'll be there any time between 4 and 10 p.m. because I'm really uncertain about time. Well, that would be bad. This is pretty bad too. To be 42% uncertain when the numbers you used were only 0.25% and 0.5% uncertain, obviously we've done something wrong. This is not the way to deal with uncertainties when you divide. You do not just divide the numbers the way you divided the best guesses. What do you do? What is the correct way? I'll do that in blue so you can keep them straight. Well, you do compute these percentages as I mentioned earlier. However, you add the percentage uncertainties. 0.25% plus 0.58%. What does that give you? That gives you a 3 and an 8 and a 0. That feels better. This is the percentage that gets tacked on to your best guess. So if this is going to be 1.46 centimeters per second, you now go plus or minus 0.83%. That looks a lot better. And you can also convert this back into centimeters per second. 0.83 times 1.46 divided by 100, that'll give you 0.83% of 1.46. So let's do that. 0.83 times 1.46 divided by 100, and now we see that we're actually dealing with 0.01. Okay, so 1.46 centimeters per second plus or minus not even a percentage, not even 1%, 0.01 centimeters per second. So folks, we have a name for this. We call this a percent uncertainty, also known as a relative uncertainty or relative error. And when we convert back into the actual units, we call that absolute form, the absolute uncertainty. And the rule for dividing is to get your uncertainties into percent form, relative form, and add those. They add to the percentage, which is the relative uncertainty of your calculated number. And if you want, you can convert that back to absolute form. Good news, when you multiply two numbers, as in area equals length times width, oh, I got to multiply two measured numbers, same thing. Add the percent uncertainties. All right, that's about it. Getting back to here, have we done what we accomplished? Yes. We talked about what uncertainties are and why they arise and how you can't really avoid them, no matter how hard you try. And we also talked about how to do calculations like add, subtract, multiply, divide with uncertainties. And now you can go practice some more of that in course pack page 7 to 12. Thanks for watching, folks. Have a nice day. I'll see you in the next video.